What if everything you have ever seen, touched, or even imagined once never existed? What if there was a time when even the smallest building blocks of reality, the atoms themselves, were just nothing? How did something so fundamental emerge from absolute emptiness? To truly understand this, we have to go back, not just millions or billions of years, but to the very beginning, when the universe itself was born. Scientists believe the universe began 13.8 billion years ago with the Big Bang. But what does that mean? It wasn't an explosion in space, it was the expansion of space itself from an infinitely small point. Imagine all the energy and matter that make up the universe today compressed into an unimaginably tiny, dense, and hot singularity. In that moment, time and space as we know them came into existence. The first fraction of a second after the Big Bang was chaotic beyond comprehension. The universe was in a state of extreme heat and density, with temperatures reaching trillions of degrees. This period is known as the Planck epoch, named after physicist Max Planck. During this time, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified into a single force. Scientists theorize that as the universe expanded, these forces began to separate, setting the stage for the formation of matter as we know it. Matter and energy were indistinguishable in this early phase. Energy fluctuations at the quantum level gave rise to pairs of particles and antiparticles, which would instantly annihilate each other. However, for reasons not yet fully understood, a slight imbalance favored matter over antimatter. This tiny asymmetry, perhaps as little as one extra matter particle per billion, meant that when most particles and antiparticles annihilated each other, a small amount of matter remained. This excess matter became the foundation for the entire universe. As the universe expanded and cooled, subatomic particles began to take shape. The first fundamental particles to emerge were quarks and leptons. Quarks combined in specific ways to form protons and neutrons, while electrons, which are a type of lepton, remained separate for the time being. However, these protons and neutrons could not yet form stable atomic nuclei because the universe was still too hot. Instead, a dense, high-energy plasma filled the cosmos, where particles continuously collided, broke apart, and recombined. During this time, the universe was essentially a vast sea of radiation and energetic particles. It was an environment of constant transformation, where high-energy photons, the particles of light, interacted with matter in a way that prevented atoms from forming. This phase lasted for several 100,000 years, keeping the universe in a state of extreme instability. As the universe continued to expand, it gradually cooled. About 380,000 years after the Big Bang, the temperature had dropped enough for protons and neutrons to finally capture electrons, forming the first stable atoms. This process is called recombination. The majority of these newly formed atoms were hydrogen and helium, the simplest and most abundant elements in the universe. With the formation of atoms, light was finally able to travel freely through space, creating what scientists observe today as the cosmic microwave background radiation, a faint remnant of the Big Bang. Although atoms had formed, the universe remained dark for millions of years. This period, known as the Cosmic Dark Ages, persisted until the first stars ignited. Gravity slowly pulled together clouds of hydrogen and helium, causing them to collapse under their own weight. As pressure and temperature increased, nuclear fusion began, marking the birth of the first stars. These stars not only illuminated the cosmos, but also acted as the first factories of heavier elements. Through nuclear fusion, hydrogen atoms combined to form helium, and in the cores of massive stars, elements like carbon, oxygen, and iron were forged. When these early stars reached the end of their lives, many exploded in spectacular supernovae, scattering their enriched contents across the universe. These explosions seeded the cosmos with heavier elements, which would later become the building blocks of planets, moons, and even life itself. Every atom in our bodies, from the oxygen we breathe to the calcium in our bones, was once formed in the heart of a dying star. As galaxies began to form, the process of star formation continued, creating new generations of stars and planetary systems. The vast cosmic web of matter shaped itself into clusters, filaments, and voids, giving the universe its large-scale structure. Today, the atoms that were once part of distant stars now exist in everything around us, from the air we breathe to the devices we use. The journey from the chaotic infancy of the universe to the structured cosmos we see today is a remarkable story of transformation. From the raw energy of the Big Bang to the formation of atoms, stars, and planets, the universe has undergone an extraordinary evolution. And yet, the story is still unfolding. Scientists continue to explore the mysteries of matter, energy, and the forces that govern the cosmos, seeking to understand not only where we came from, but where we are headed. So, when we ask how atoms formed from nothing, we are really asking how the universe itself came to be. The answer lies in the fundamental laws of physics, the delicate balance of forces, and the incredible processes that have shaped our reality over billions of years. In the beginning, there was nothing, not in the way we usually think of it, but rather an absence of space, time, and matter. Then, in an instant, the Big Bang occurred, unleashing an unimaginable burst of energy that would go on to create everything we know. This energy didn't just expand outward, it also cooled, allowing the formation of the first subatomic particles, quarks and leptons. These particles were the essential ingredients for matter, but the early universe was chaotic, with extreme heat and density keeping everything in a turbulent state. As the universe continued to expand and cool, quarks began to bind together to form protons and neutrons. This process, known as nucleosynthesis, happened within the first few minutes of the universe's existence. However, the universe was still too hot for atoms to form. Instead, these protons and neutrons remained in a high-energy plasma, constantly colliding and interacting. It took nearly 380,000 years for the universe to cool down enough for electrons to slow down and be captured by protons, forming the first true atoms, mostly hydrogen and helium. This event, called recombination, allowed light to finally travel freely, creating what we now see as the cosmic microwave background radiation. This faint glow is a remnant of the early universe, providing a snapshot of how things looked shortly after atoms first formed. But even with atoms in place, the universe remained dark and featureless. It took millions of years for gravity to start pulling these atoms together, forming the first stars and galaxies. Inside these stars, nuclear fusion created heavier elements, including carbon, oxygen, and iron, the essential building blocks of planets, life, and even us. Every atom in your body, every breath you take, every material object around you is a result of this long cosmic journey. From the fiery birth of the universe to the formation of galaxies and the evolution of life itself, atoms have persisted, transforming and recombining in countless ways. The next time you look at the world around you, remember that everything you see, touch, and even think is made of atoms. Tiny relics of a cosmic journey that began nearly 14 billion years ago. Around 13.8 billion years ago, in a moment we call the Big Bang, something changed. A singularity, infinitely dense and hot, erupted into existence. But what caused it? This remains one of the biggest mysteries in cosmology. Some theories suggest that a quantum fluctuation in an unstable vacuum led to the explosion that became our universe. Others propose that the Big Bang was just one phase in an eternal cycle of expansion and contraction. In less than a trillionth of a second, the universe expanded at an incomprehensible rate. This period, known as cosmic inflation, saw the universe grow exponentially, stretching space itself. To put this in perspective, imagine taking a single atom and expanding it to the size of the observable universe almost instantly. That's how dramatic this event was. This inflationary period smoothed out the fabric of space, creating the conditions necessary for structure to form later on. Tiny fluctuations in the density of matter, imprinted by quantum mechanics, were stretched to cosmic scales. These fluctuations would later become the seeds of galaxies, stars, and planets. But despite this rapid expansion, there was no structure, no atoms, only an intense energy field that would later give birth to all known matter. The energy that filled the universe during inflation eventually converted into a hot, dense plasma of particles. This process, called reheating, marked the beginning of the universe as we recognize it. During these first crucial moments, all four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified. As the universe cooled, they separated, each playing a distinct role in shaping the cosmos. Gravity pulled matter together, the strong force bound atomic nuclei. Electromagnetism governed interactions between charged particles, and the weak force allowed for nuclear reactions and decay processes. For the first fraction of a second, the universe was a chaotic soup of high-energy particles. These included quarks, the building blocks of protons and neutrons, and leptons, which include electrons. The interactions between these particles were governed by the laws of quantum mechanics, with countless collisions occurring every moment. For the first fraction of a second, the universe was a chaotic soup of high-energy particles. These included quarks, the building blocks of protons and neutrons, and leptons, which include electrons. The interactions between these particles were governed by the laws of quantum mechanics, with countless collisions occurring every moment. At this stage, something extraordinary happened. Matter and antimatter were created in almost equal amounts. For every particle of matter, there was an antiparticle with the same mass but opposite charge. When these pairs collided, they annihilated each other in bursts of energy. If there had been perfect symmetry between matter and antimatter, they would have completely cancelled out, leaving behind only radiation. But for reasons still not fully understood, a tiny imbalance favored matter. For every billion antimatter particles, there was one extra matter particle. This slight excess is what allowed matter to dominate and eventually form the universe we know today. As the universe continued to expand and cool, quarks began to combine, forming the first protons and neutrons. These fundamental particles were the building blocks of atomic nuclei. However, the universe was still too hot for them to come together into stable atoms. Instead, they existed in a high-energy plasma, constantly interacting with photons, the particles of light. This early plasma was so dense that photons couldn't travel freely. Instead, they scattered off electrons, creating an opaque, fog-like state. It wasn't until hundreds of thousands of years later that the universe would cool enough for atoms to form, allowing light to travel freely for the first time. The formation of protons and neutrons marked a critical turning point. These particles would later combine in a process called nucleosynthesis, creating the first atomic nuclei. However, before full-fledged atoms could form, the universe had to cool even further. The next stage of this cosmic story would see the emergence of the very first elements, hydrogen and helium, laying the foundation for everything that followed. To truly appreciate this stage, we have to consider the extreme conditions of the early universe. At just a few millionths of a second old, temperatures were trillions of degrees, far hotter than the core of even the most massive stars today. In this environment, protons and neutrons formed, but the energy levels were so high that they were constantly being torn apart again. Only as the universe expanded and cooled did these particles become stable. One of the most crucial events during this phase was the fusion of protons and neutrons into larger atomic nuclei. This process, known as Big Bang nucleosynthesis, took place within the first 3 minutes of cosmic history. During this time, simple atomic nuclei such as hydrogen, a single proton, and helium, 2 protons and 2 neutrons, formed. A small amount of lithium and beryllium also emerged, though in much smaller quantities. The abundance of these elements is a direct result of the conditions present in the early universe. The reason hydrogen and helium dominate the cosmos today is that heavier elements require much longer timescales and different conditions to form, conditions that would only arise later in the cores of stars. Even after these nuclei formed, full-fledged atoms still couldn't exist. Electrons, which are much lighter than protons and neutrons, were still too energetic to be captured into stable orbits. The universe remained in a hot, ionized state, meaning that atomic nuclei and free electrons floated separately, unable to bond into neutral atoms. This period of the universe was effectively a cosmic fog. Photons, or particles of light, continuously bounced off free electrons, preventing them from traveling far. As a result, the universe was opaque, meaning that light couldn't move freely through space. It took nearly 380,000 years for the universe to cool down enough for electrons to slow down and be captured by atomic nuclei. This moment is known as recombination. For the first time, neutral atoms, mostly hydrogen and helium, could form. With electrons now bound to nuclei, light could travel freely across space, leading to the release of the cosmic microwave background radiation, a faint glow that still exists today and serves as one of the most important pieces of evidence for the Big Bang. The formation of these first atoms was a defining moment in cosmic history. It set the stage for the large-scale structure of the universe, allowing gravity to begin pulling these atoms together into dense regions that would eventually form galaxies, stars, and planets. But the story of atoms was far from over. The universe was still a vast, dark, and largely featureless expanse. The atoms that had just formed were spread thinly across space, with no structures yet in place. It would take millions of years for gravity to begin pulling these atoms together, creating the first stars and galaxies. This phase of the universe, known as the Cosmic Dark Ages, was a time of waiting. There were no stars to shine, no galaxies to illuminate space, just the slow, patient pull of gravity working in the background. Over time, denser regions of hydrogen and helium began to collapse under their own gravity, forming the first protostars. The formation of the first stars would mark the next major transformation of the universe. These early stars, much more massive and short-lived than the ones we see today, would become the factories for heavier elements, forging the ingredients necessary for planets, life, and even us. Understanding these early moments of the universe helps us grasp the immense complexity and precision required for the existence of atoms. Without the right balance of forces, the right initial conditions, and the tiny asymmetry that favored matter, the universe as we know it wouldn't exist. Every atom in your body owes its existence to these first few moments after the Big Bang, when the fundamental ingredients of reality were forged in the cosmic furnace of creation. The story of atoms doesn't end here. In the next section, we'll explore how these atomic nuclei combined with electrons to form the first true atoms, and how these atoms set the stage for the formation of stars, galaxies, and eventually life itself. The universe, now filled with newly formed hydrogen and helium atoms, was no longer an opaque plasma, but a vast, dark expanse. With light finally free to travel, the cosmos was illuminated by the afterglow of the Big Bang, known as the cosmic microwave background radiation. However, despite this newfound transparency, there were no stars, no galaxies, just an immense sea of gas waiting for something extraordinary to happen. Gravity, the silent architect of the universe, began its slow and steady work. Over millions of years, tiny fluctuations in the density of matter allowed some regions to become slightly denser than others. These denser pockets of hydrogen and helium began to attract more and more matter due to their gravitational pull, leading to the formation of the first cosmic structures. As these clouds of gas grew denser, their internal pressure increased, causing temperatures to rise. Eventually, deep within these collapsing clouds, temperatures and pressures became so extreme that nuclear fusion ignited the birth of the first stars. These primordial stars, known as population 3 stars, were vastly different from the stars we see today. They were massive, burning at incredibly high temperatures, and lived for only a few million years before exploding in spectacular supernovae. These first stars played a crucial role in shaping the universe. Through nuclear fusion, they began creating elements heavier than hydrogen and helium, including carbon, oxygen, and even iron. When these stars reached the end of their lives and exploded, they scattered these elements across space, seeding future generations of stars, planets, and ultimately, life itself. But what made these early stars so unique? Unlike the stars we see today, which contain heavier elements from previous generations, the first stars formed purely from hydrogen and helium. This meant they could grow to enormous sizes, some even hundreds of times the mass of our Sun. These gigantic stars burned their fuel incredibly quickly, producing immense amounts of ultraviolet radiation, which began to ionize the surrounding hydrogen gas, marking the beginning of the epoch known as cosmic reionization. Cosmic reionization was a crucial transition in the history of the universe. As the first stars and galaxies emerged, their intense radiation started stripping electrons away from neutral hydrogen atoms, turning the universe back into a state of ionized gas. This process took hundreds of millions of years, but it gradually cleared the universe of the remaining cosmic fog, allowing light from newly forming galaxies to travel freely through space. Meanwhile, gravity continued to shape the young universe, pulling stars together into the first galaxies. These galaxies were much smaller and irregularly shaped compared to the majestic spiral and elliptical galaxies we see today. Over time, they merged and evolved, growing into the vast cosmic structures that now fill the universe. The role of dark matter in this process cannot be overlooked. Though invisible and mysterious, dark matter exerted a strong gravitational pull, helping to speed up the formation of galaxies by acting as a cosmic scaffold. Without dark matter, the universe as we know it might have taken far longer to develop into its current state. As the first stars aged and exploded in violent supernovae, triggering the formation of new stars in surrounding gas clouds. These supernovae also played a critical role in enriching the universe with heavier elements, laying the foundation for future planetary systems and, ultimately, life itself. As the first stars aged and exploded in violent supernovae, they released enormous amounts of energy, triggering the formation of new stars in surrounding gas clouds. These supernovae also played a critical role in enriching the universe with heavier elements, laying the foundation for future planetary systems and, ultimately, life itself. The formation of the first galaxies marked the beginning of a new cosmic era. These early galaxies were chaotic and rapidly evolving, but they set the stage for the grand structures we see today: galaxy clusters, superclusters, and the vast cosmic web that stretches across the universe. The universe was no longer a dark, empty expanse. It had entered a new phase, one where light, structure, and complexity began to emerge on a grand scale. The stage was now set for the formation of solar systems, planets, and the intricate web of cosmic evolution that would eventually lead to the formation of Earth and everything on it. As we move forward in our journey, we will explore how these stars and galaxies continue to evolve, how planetary systems like our own took shape, and how the fundamental elements forged in the hearts of stars eventually came together to form the building blocks of life. The story of the universe is far from over. It is a continuous, unfolding narrative, and we are just beginning to understand our place within it. Over billions of years, gravity continued to sculpt the cosmos. Galaxies merged, collided, and evolved, forming dazzling spiral and elliptical shapes. These grand interactions played a crucial role in redistributing matter and setting the stage for the formation of more complex celestial bodies. Supermassive black holes formed at the centers of many galaxies, shaping their evolution through intense gravitational interactions and high-energy emissions. These powerful cosmic engines influence the movement of stars and the growth of galaxies, creating some of the most energetic phenomena in the universe, such as quasars and active galactic nuclei. In time, within the swirling arms of galaxies, stars began forming in vast stellar nurseries, regions filled with gas and dust. Some of these stars were accompanied by rotating disks of material, from which planets and moons eventually coalesced. This was the beginning of solar systems like our own, marking yet another pivotal chapter in the grand story of the universe. As galaxies matured and stabilized, the elements produced in earlier generations of stars became more abundant. Heavier elements, such as carbon, oxygen, and iron, were scattered across the cosmos, becoming the raw materials from which rocky planets and eventually living organisms would emerge. From the simplest atoms formed after the Big Bang to the vast cosmic structures of today, the universe has undergone an extraordinary transformation. What began as a uniform expanse of hydrogen and helium has evolved into a rich and diverse cosmos filled with galaxies, stars, planets, and even conscious beings capable of contemplating their own origins. The journey of the universe is a testament to the intricate interplay of physics, time, and chance. And as we continue to explore, we uncover deeper mysteries, questions about dark energy, the fate of the cosmos, and the possibility of life beyond our own world. The story is far from over, and every new discovery brings us closer to understanding the grand tapestry of existence. As the first stars ignited, they unleashed an immense amount of energy, flooding the universe with ultraviolet light. This era, known as the Epoch of Rayonization, marked a crucial turning point. The intense radiation from these early stars stripped electrons from surrounding hydrogen atoms, ionizing the gas and making the universe transparent once again. This process took hundreds of millions of years, gradually clearing the cosmic fog and allowing galaxies to shine more brightly. With rayonization underway, stars began to cluster together due to gravity, forming the earliest galaxies. These galaxies were small and irregular, a far cry from the majestic spiral and elliptical galaxies we see today. Over time, smaller galaxies merged, colliding and combining their mass to form larger, more structured galaxies. This chaotic period of mergers and interactions played a crucial role in shaping the large-scale structures of the universe. At the center of many of these young galaxies, something even more mysterious was taking shape: supermassive black holes. These black holes, millions or even billions of times the mass of the Sun, grew rapidly as they consumed gas and stars. As material spiraled into these black holes, it formed extremely hot, glowing disks of matter, creating some of the brightest objects in the universe, quasars. These quasars lit up the early cosmos, acting as beacons that we can still observe today, providing a glimpse into the universe's infancy. Meanwhile, inside the first galaxies, new generations of stars were forming. Unlike the massive, short-lived population 3 stars, these new stars contained heavier elements produced in earlier supernova explosions. These elements, carbon, oxygen, nitrogen, and iron, would become the building blocks for planets, moons, and eventually life itself. As galaxies continued to evolve, they organized into massive cosmic structures, forming galaxy clusters and superclusters interconnected by vast filaments of dark matter. The cosmic web began to take shape, defining the large-scale structure of the universe that we observe today. The formation of these structures set the stage for the next great chapter in cosmic history: the birth of solar systems, planetary formation, and the long journey toward life. The story of the universe was still unfolding, but by this point, the fundamental ingredients were in place. The elements forged in the hearts of dying stars would soon find themselves forming new celestial bodies. In the next section, we will explore how planets took shape, how solar systems formed around young stars, and how Earth itself emerged as a tiny but remarkable world in the vastness of space. The formation of black holes at the centers of many galaxies played a crucial role in shaping the cosmic environment. These supermassive black holes, millions to billions of times the mass of the Sun, formed through the collapse of massive stars or by the gradual accumulation of matter over time. As gas and dust spiraled into these black holes, the extreme gravitational forces heated the material, causing it to emit immense amounts of energy in the form of radiation and powerful jets. Some black holes became active galactic nuclei or quasars, outshining entire galaxies. These interactions significantly influenced their host galaxies. The energy released by black holes could either trigger or suppress star formation. Powerful outflows and radiation could heat surrounding gas, preventing it from collapsing into new stars, while in some cases, shockwaves compressed gas clouds, leading to star formation. This feedback mechanism played a major role in determining the structure and evolution of galaxies. At the same time, the universe took on a larger structure known as the cosmic web, a vast network of interconnected filaments made of galaxies and dark matter. Gravity pulled matter together over billions of years, forming this intricate web. Dense regions became galaxy clusters, while elongated filaments connected them, and immense voids separated these structures. Dark matter acted as a gravitational framework, guiding the formation of galaxies along these filaments. Within this cosmic web, the Milky Way galaxy took shape, providing the foundation for the solar system and Earth. As galaxies evolved, they enriched the universe with heavier elements through the life cycles of stars. The first stars were massive and short-lived, producing elements like carbon, oxygen, and iron when they exploded as supernovae. These materials mixed with interstellar gas, creating the building blocks for future generations of stars and planets. The Milky Way developed into a spiral galaxy, and within one of its star-forming regions, the solar system began to take shape. The presence of the parent star played a significant role in shaping the evolution of planetary systems. Young stars emitted intense radiation and powerful stellar winds, which could strip away the atmospheres of nearby planets or clear excess gas and dust from the protoplanetary disk. This process determined which planets retained their atmospheres and which ones became barren. Additionally, the gravitational influence of massive planets like Jupiter had a profound effect on the structure of the solar system. Jupiter's immense gravity acted as a protector, preventing large numbers of asteroids and comets from reaching the inner solar system, but it also contributed to violent periods of planetary collisions and migrations that reshaped the orbits of many celestial bodies. While planetary systems formed throughout the universe, only a few had the precise conditions necessary for life to emerge. In the case of our own solar system, Earth was fortunate enough to be located within what is known as the habitable zone, the region around a star where temperatures are just right for liquid water to exist. This was a crucial factor in the development of life. Additionally, Earth's composition was enriched by elements that had been forged in previous generations of stars, providing the right conditions for complex chemistry to take place. As the early Earth evolved, its molten surface gradually cooled, allowing a solid crust to form. Intense volcanic activity released gases into the atmosphere, which contributed to the formation of a stable climate. Water vapor, which had been trapped within the planet, eventually condensed to form the first oceans. The presence of liquid water was a key factor in enabling chemical reactions that would lead to the development of organic molecules. These molecules, through billions of years of interaction and gradual complexity, eventually gave rise to the first primitive life forms. These early organisms were simple, single-celled life forms that thrived in Earth's oceans. Over time, through the processes of evolution and natural selection, they diversified and adapted to their environments. Some developed the ability to photosynthesize, harnessing sunlight to produce energy and oxygen. This led to a dramatic transformation of Earth's atmosphere, paving the way for more complex life forms to emerge. Eventually, multicellular organisms evolved, leading to the incredible diversity of life that exists today. The story of planetary formation is deeply interconnected with the broader cosmic processes that shape the universe. From the birth of stars to the formation of galaxies and the enrichment of space with heavy elements, each step played a role in creating the conditions necessary for planets and life. The journey from tiny dust particles to fully formed planets was a long and intricate process, guided by the fundamental forces of nature and the delicate balance of cosmic interactions. Even today, the universe continues to form new planetary systems, offering scientists valuable insights into the processes that shaped our own solar system. By studying exoplanets, planets that orbit stars beyond our sun, astronomers have discovered an incredible variety of planetary systems, some similar to our own and others vastly different. Some exoplanets orbit extremely close to their stars, experiencing intense heat, while others exist in the cold darkness of interstellar space after being ejected from their original systems. These discoveries continue to reshape our understanding of planet formation and the potential for habitable worlds beyond Earth. As we explore the cosmos, we gain a deeper appreciation of our place in the universe. The formation of planets, the emergence of life, and the ongoing search for habitable worlds all contribute to the vast and ever-evolving story of the cosmos. While Earth remains the only known planet to host life, the universe is vast, and the possibilities are endless. Our quest to understand the origins of planetary systems and the conditions necessary for life is far from over. Each new discovery brings us closer to answering one of the most profound questions of all. Are we alone in the universe? The process that led to the formation of planetary systems began with the birth and evolution of galaxies and stars, which laid the foundation for everything that would come later. In the earliest stages of the universe, vast clouds of gas and dust gradually collapsed under their own gravity, forming the first stars. These stars were mostly composed of hydrogen and helium, the two lightest and most abundant elements created in the aftermath of the Big Bang. These early stars, known as population 3 stars, were much larger and hotter than the stars we see today, burning through their fuel at an incredible rate. Because they lacked heavier elements, their internal processes were different from those of later stars, but they still played a crucial role in shaping the cosmos. Over time, through nuclear fusion in their cores, these stars produced heavier elements such as carbon, oxygen, silicon, and iron. The process of fusion is what powered these stars, allowing them to shine and generate immense energy. However, the fuel supply within a star is not infinite. When massive stars reached the end of their life cycle, they underwent dramatic transformations. Some stars expanded into red giants before shedding their outer layers, while others exploded as supernovae, dispersing their newly forged elements across space. These supernovae were among the most powerful explosions in the universe, capable of outshining entire galaxies for a brief period. They not only enriched interstellar gas clouds with the essential ingredients for planet formation, but also triggered new waves of star formation by compressing nearby clouds of gas and dust. As time passed, the cycle of starbirth and death continued, gradually increasing the abundance of heavy elements in the universe. These elements played a crucial role in the formation of planetary systems because they provided the necessary building blocks for solid planets, moons, and other celestial bodies. In regions where interstellar gas and dust were abundant, gravity began to pull material together, forming massive rotating clouds known as nebulae. Within these nebulae, denser regions began to collapse, giving rise to new stars. Around these young stars, disks of leftover material, called protoplanetary disks, began to form. These disks contained a mixture of microscopic dust grains, volatile gases, and heavier elements that had been created in previous generations of stars. Within these swirling disks, small solid particles started to collide and stick together due to electrostatic forces. Initially, these particles were no larger than specks of dust, but as they continued to merge, they gradually formed larger and larger clumps. This marked the earliest stage of planetary formation. Over thousands to millions of years, some of these clumps grew into pebble-sized objects, which then collided to form even larger bodies. Eventually, these bodies became planetesimals, small celestial objects that served as the building blocks of planets. Some planetesimals were destroyed in high-speed collisions, breaking apart into smaller fragments that either reaccumulated or were scattered into space. However, others continued to grow, setting the stage for the formation of full-size planets. The process by which planetesimals grew into protoplanets was driven by a mechanism known as accretion. Accretion is the process by which gravity pulls together gas, dust, and rock, allowing objects to increase in size over time. As these protoplanets formed, their gravitational fields became stronger, allowing them to attract even more material. In regions close to the central star, where temperatures were extremely high, volatile substances such as water, methane, and ammonia were unable to condense into solid form. As a result, the planets that formed in these regions were primarily composed of rock and metal. These became the terrestrial planets, like Mercury, Venus, Earth, and Mars. In the colder outer regions of the protoplanetary disk, where temperatures were low enough for gases and ices to remain stable, a different type of planetary formation took place. Massive planets like Jupiter and Saturn formed by accumulating large amounts of hydrogen and helium, the same elements that made up the Sun. These gas giants grew much larger than the rocky planets because they had access to an abundance of material in the outer disk. Additionally, their strong gravitational fields allowed them to capture and retain thick atmospheres, making them fundamentally different from the smaller, denser terrestrial planets. Beyond the gas giants, even farther from the Sun, icy bodies and dwarf planets formed in the Kuiper Belt, a vast region filled with frozen remnants from the early solar system. With the formation of planetary systems, the stage was set for even more complexity to emerge. In the vast swirling disks of gas and dust surrounding young stars, countless chemical reactions began to take place. These reactions were influenced by a variety of factors, including temperature, pressure, radiation, and the presence of different elements. Simple molecules such as water, carbon dioxide, methane, and ammonia began to form, laying the foundation for more intricate chemical processes. These molecules, though basic, were crucial components that would eventually lead to the emergence of life. The presence of these molecules in interstellar space has been confirmed through astronomical observations, revealing that complex chemistry is not unique to Earth. Even within the cold, vast voids between stars, reactions occur that give rise to organic compounds. In protoplanetary disks, where conditions were more conducive to chemical evolution, these molecules began interacting and combining into more complex structures. Over time, these reactions produced amino acids, nucleotides, and other organic compounds, which are the fundamental building blocks of life. The exact mechanism by which life emerged from these molecules remains one of the greatest mysteries in science. Several theories have been proposed to explain how simple chemical reactions eventually led to self-replicating systems capable of evolution. One prominent hypothesis suggests that life may have originated in deep-sea hydrothermal vents. These vents, found along the ocean floor, release mineral-rich water heated by geothermal energy. The extreme conditions within these vents, high temperatures, pressure gradients, and the presence of catalytically active minerals, could have provided the necessary environment for simple organic molecules to assemble into more complex structures. The energy provided by these vents would have allowed chemical reactions to take place, leading to the formation of primitive metabolic pathways. Another compelling theory suggests that life may have begun in shallow tidal pools, where cycles of wetting and drying could have played a crucial role in the concentration and polymerization of organic molecules. The intermittent exposure to sunlight and variations in environmental conditions might have driven the formation of increasingly complex biomolecules. This scenario suggests that life may have originated on land or in coastal environments rather than deep in the oceans. Some scientists propose that the building blocks of life may have arrived from space, carried by comets, asteroids, and interstellar dust. This idea, known as panspermia, posits that organic molecules formed in space and were delivered to early Earth through meteorite impacts. Evidence supporting this theory comes from the discovery of amino acids and other organic compounds in meteorites and comets. If this theory is correct, it suggests that the origins of life might not be unique to Earth, but could be a common occurrence throughout the universe. Regardless of where life first began, the next step in its evolution was the transition from simple organic molecules to self-replicating entities. At some point, certain molecular structures gained the ability to copy themselves, leading to the first primitive cells. These early forms of life were likely simple, single-celled organisms that relied on basic metabolic processes to harness energy from their surroundings. They may have used chemical gradients, sunlight, or other sources of energy to sustain themselves and reproduce. Over millions of years, evolutionary pressures drove these early organisms to become more complex. Mutations and genetic variations led to adaptations that allowed them to survive in different environments. Some of these organisms developed photosynthesis, a process that allowed them to harness the energy of sunlight to produce food. This was a crucial turning point in the history of life, as it led to the release of oxygen into the atmosphere, fundamentally altering the chemistry of Earth. As oxygen levels increased, new opportunities arose for the evolution of more complex life forms. Some organisms began using oxygen for respiration, which provided them with a more efficient way to generate energy. This allowed for the development of larger and more intricate multicellular organisms. Over time, life diversified into an astonishing array of forms, filling every available ecological niche on the planet. The transition from chemistry to biology was a gradual and intricate process shaped by countless environmental factors and chance events. While the precise details of how life first arose remain unclear, what is certain is that the conditions provided by early Earth were crucial in fostering the emergence of living systems. The interplay of physics, chemistry, and biology worked together in an intricate dance, gradually transforming the raw materials of the cosmos into S. Understanding the origins of life also provides insight into the broader question of our place in the universe. If life emerged on Earth through natural processes, it raises the possibility that similar processes could occur elsewhere. The discovery of exoplanets, planets orbiting other stars, has revealed that many of them exist within the habitable zones of their respective stars, where conditions might be suitable for life. Some of these planets have atmospheres that contain water vapor, methane, and other compounds that are associated with biological activity. While we have yet to discover definitive evidence of extraterrestrial life, the possibility remains tantalizing. If life exists elsewhere, it may take many different forms, shaped by the specific conditions of each world. Some planets may host microbial life in underground oceans, while others could have developed entirely different biochemical processes to sustain living organisms. The sheer number of stars in the universe suggests that, statistically, life beyond Earth may not only be possible, but highly probable. Scientists continue to refine their methods of detecting potential biosignatures, looking for chemical imbalances in planetary atmospheres that could indicate biological activity. As technology advances, our ability to probe deeper into space will bring us closer to answering one of humanity's oldest and most profound questions: are we alone in the universe? As we explore the cosmos, we gain a deeper appreciation of the interconnectedness of all things. The atoms that make up our bodies were forged in the hearts of ancient stars, scattered across the universe by supernova, and eventually incorporated into the Earth and everything on it. The same forces that govern the motions of galaxies also dictate the chemical reactions in our cells. By studying the history of the universe, we come to understand the profound relationship between the cosmos and ourselves. Every living being is a part of this grand cosmic cycle, where matter is continuously recycled, forming new stars, planets, and, potentially, life. The realization that everything we see, touch, and experience is the product of an ancient and ongoing process highlights the deep connection between the universe and life itself. Each discovery we make brings us closer to understanding not only our physical origins, but also the fundamental principles that shape existence. The story of atoms and life is one of transformation, adaptation, and evolution. From the birth of the first stars to the formation of planets and the emergence of biological systems, each stage has built upon the previous one in an unbroken chain of events that stretches back nearly 14 billion years. By understanding this journey, we gain not only scientific knowledge, but also a greater appreciation for the extraordinary sequence of events that made our existence possible. Every element in our bodies, every drop of water, and every breath we take is part of a cosmic narrative that extends beyond our planet and into the farthest reaches of space. Life, in many ways, is an extension of the universe's ongoing evolution, adapting to and shaping the environment it inhabits. As we look to the future, the search for life beyond Earth continues. Missions to Mars, Europa, and Enceladus seek to uncover signs of past or present microbial life, while telescopes scan distant exoplanets for potential biosignatures. The discovery of life elsewhere in the universe would be one of the most profound scientific breakthroughs in history, confirming that we are not alone and that life is a fundamental feature of the cosmos. The implications of such a discovery would extend beyond science, reshaping philosophy, religion, and our understanding of what it means to be alive. It would force us to reconsider our uniqueness and our responsibilities as stewards of our own planet. If life exists elsewhere, it may be vastly different from anything we have ever encountered, challenging our definitions and perceptions of biology itself. The ongoing advancements in space exploration and astrobiology ensure that we are closer than ever to solving this grand mystery. In the end, the exploration of our cosmic origins is not just a scientific endeavor, but a deeply philosophical one. It forces us to confront fundamental questions about who we are, where we come from, and what our place is in the grand tapestry of existence. While many mysteries remain, one thing is certain: the journey from atoms to life is one of the most remarkable and awe-inspiring stories ever told. The more we learn, the more we realize how much remains unknown, and yet each discovery brings us a step closer to understanding the full magnitude of our existence. Whether life is a rare anomaly or a widespread cosmic phenomenon, as we reach the final stretch of our journey through the origins of atoms and the grand story of the universe, it's time to step back and reflect on what we've uncovered. From the earliest moments of the cosmos, when energy transformed into matter, to the formation of the first atomic structures, stars, and galaxies, we have witnessed an extraordinary sequence of events that led to the existence of everything we know today, including ourselves. The birth of atoms was not just a random occurrence. It was the product of fundamental forces working in perfect harmony. Gravity, electromagnetism, and nuclear forces all played crucial roles in shaping the cosmos. The tiniest asymmetry between matter and antimatter ensured that some matter remained after the Big Bang, allowing atoms to exist. The nuclear reactions within the hearts of stars forged heavier elements, seeding the universe with the necessary ingredients for planets, life, and ultimately consciousness. Without this intricate sequence of events, our world would not exist. The atoms in our bodies, carbon, oxygen, nitrogen, and so many others, were all formed in ancient stars that lived and died billions of years ago. Every breath we take, every thought we have, and every action we perform is powered by these fundamental building blocks, making us deeply connected to the vast, ever-expanding universe. But even as we marvel at what has already happened, it's essential to recognize that the story of atoms and the universe is far from over. The cosmos continues to evolve. New stars are born, galaxies collide, and elements are continuously cycled through cosmic processes. The expansion of the universe is still ongoing, and dark energy remains one of the greatest mysteries, driving this expansion at an accelerating rate. The future of the universe is uncertain. Will it expand forever, slow down, or eventually collapse? Scientists continue to seek answers, and each new discovery brings us closer to understanding our cosmic fate. At the heart of all of this is the simple yet profound fact that we, as human beings, are not separate from the universe. We are products of it. Our curiosity, our drive to explore, and our desire to understand our origins are all testaments to the incredible journey that matter has taken over billions of years. From the smallest subatomic particles to the grandest cosmic structures, we are part of something vast, intricate, and awe-inspiring. So, the next time you look up at the night sky, remember that you are looking at the same fundamental elements that make up your very being. The hydrogen in the stars is the same hydrogen found in the water you drink. The iron in your blood once resided in the core of an ancient star. Every atom in your body has traveled through time and space, shaped by the universe's grand and magnificent journey. This realization gives rise to an even deeper question. What does this cosmic connection mean for us as individuals? If we are made of stardust, then in a way, we are not just observers of the universe, we are an expression of the universe itself. Our existence is a direct result of the fundamental processes that have governed the cosmos since the beginning of time. The laws of physics, chemistry, and biology that shape the stars and galaxies are the same laws that gave rise to life, intelligence, and consciousness. In this sense, our journey to understand atoms is not just a scientific endeavor, it is a quest to understand ourselves and our place in the grand scheme of existence. Even now, the atoms that compose our bodies are not static. They are in a constant state of change, cycling through different forms and states. Every few years, nearly every atom in your body is replaced through the processes of metabolism and renewal. The oxygen we breathe, the food we eat, and the water we drink all carry atoms that were once part of other living beings, ancient landscapes, or even the distant cosmos. This means that, in a profound way, we are all connected, not just to the universe at large, but to each other and to all of life that has ever existed on Earth. Our journey through time does not end here. The very same forces that shaped the universe continue to shape us. Advances in science and technology allow us to peer deeper into the cosmos, uncovering secrets about the nature of reality that were once unimaginable. With powerful telescopes, we have captured images of distant galaxies whose light has traveled billions of years to reach us. We have studied the cosmic microwave background, the faint glow of the Big Bang itself, giving us a glimpse into the universe's infancy. And yet, there is still so much more to learn. The search for extraterrestrial life represents one of the most profound and exciting frontiers in human exploration. For centuries, humans have gazed at the stars, wondering if life exists beyond our planet. This question has fascinated philosophers, scientists, and dreamers alike, driving scientific inquiry and technological advancements that bring us closer to finding an answer. The fundamental principles of chemistry, physics, and biology suggest that if life on Earth arose from the same basic elements and physical laws that govern the entire universe, then the possibility of life elsewhere cannot be ignored. Given the vast number of planets in the universe, the odds suggest that at least some of them might have the right conditions for life to emerge. Scientists are particularly interested in exoplanets, which are planets orbiting stars outside our solar system. These distant worlds hold the potential to answer one of humanity's oldest and most profound questions: are we alone in the universe? To determine whether an exoplanet could support life, scientists analyze its atmosphere, temperature, and chemical composition. They look for specific signs that suggest the presence of liquid water, organic molecules, and stable climate conditions that could support biological processes. Advanced telescopes and space missions, such as the James Webb Space Telescope and exoplanet hunting satellites, are helping researchers identify planets within the habitable zone, the region around a star where conditions might allow liquid water to exist on a planet's surface. The discovery of even the simplest microbial organisms on another planet would be a groundbreaking revelation, proving that life is not unique to Earth. Such a discovery would reshape our understanding of biology, evolution, and the nature of existence itself. If life can arise elsewhere, it would suggest that the universe is teeming with life in various forms, possibly even intelligent civilizations. The implications of this realization would extend beyond science, influencing philosophy, religion, and how humanity perceives its place in the cosmos. Beyond the search for extraterrestrial life, our understanding of atoms and their interactions has played a crucial role in shaping the technological advancements that define modern civilization. Atoms, the building blocks of all matter, form the foundation of everything we see, touch, and experience. The study of atomic structures and their behavior has led to remarkable discoveries in fields such as nuclear physics, quantum mechanics, and molecular biology. These scientific breakthroughs have revolutionized energy production, medical treatments, computing, and countless other aspects of daily life. Nuclear energy, for example, provides a powerful source of electricity, harnessing the immense energy stored within atomic nuclei. Quantum mechanics, once considered purely theoretical, now forms the basis of cutting-edge technologies like quantum computing, which has the potential to revolutionize data processing and encryption. Molecular biology, guided by atomic principles, has enabled advancements in genetic engineering, medicine, and biotechnology, allowing us to manipulate DNA, create life-saving treatments, and better understand the complexity of living organisms. As humanity continues to push the boundaries of scientific discovery, future advancements in nanotechnology, space exploration, and artificial intelligence will be shaped by our ever-deepening knowledge of atomic principles.